Okay, so this is example 8.5, part B. 8-5B. And so what we have is a ramp like that and a pulley at the top. And we've got a hanging mass here. I'm going to call this mass 2. And we've got a kind of a sliding mass right here. I'm going to call that mass 1. Alright, and they're connected by a string that goes up over the pulley and down like that. Okay, so in part B, mass 1, I'm going to go ahead and write that out, is still 5.7, oh, not newtons, it's kilograms, right? 5.7 kilograms. Mass 2, I can't write today, is 15 kilograms. All right, and the question is, which way is it going to go? Is it going to rotate that way, or is it going to go that way? So, clockwise or counterclockwise? Whoops, we don't know. All right, and the other part of that is, if it whatever direction it does go, what's the acceleration of the system going to be? All right. So, let's start by labeling all of our forces right here, all right? This one right here, we've got mass 2 times gravity, pulling straight down. Mass 1 times gravity also pulls straight down, m1g, but not all of that weight is directed along the axis of motion, is it? A lot of it's directed into the table. So what we care more about is what's the force that is pulling downhill. All right, well, you know that is going to be your force parallel, right? Force parallel to the plane, which we also know to be mg sine theta. And there's also a force perpendicular. Force perpendicular directed into the plane, which is mg cosine theta, right there. Okay? There's also going to be a normal force, right? There has to be a normal force right here, because if there was no force from the plane pushing upwards, this box would sink into the ramp. So there's got to be a normal force straight up like that. And in this case, the normal force is going to be equal to the force perpendicular, right? Finally, there's going to be a kinetic friction force, which you know is the coefficient of kinetic friction times the normal force, which is really equal to the perpendicular force. The problem is we don't know which way it's going to be acting, because we don't know yet which direction the system is going to go. Is it going to go clockwise? Is it going to go counterclockwise? We don't know. Okay? So, let's ask ourselves this. I'm starting to write with my laser pointer. Which direction is it going to go? Which is greater? All right. Well, what are the two forces that are acting along the direction of motion right here? Well, we have, let's say I'm going to call, so along this axis, I'm going to call clockwise positive and counterclockwise negative. All right, so I'm just going to remind myself that's positive and that's negative. It doesn't matter. It just means that one is acting against the other one. Okay, so that means that what is the net force on that system? Okay, well, it depends on which force wins out, the weight force of this or the parallel force of that guy right there. So, we can say that the net force on the system is going to be, I'm going to say m2g, all right? This is the one that's acting in the clockwise direction. And so we're going to subtract from that the parallel force, mg, or I should say m1g sine theta. I should have written that as m1g there and m1g right here, because they're different masses. Okay? So here's where we find out what is greater. All right? Which direction is going to move? Okay? So m2g So that's going to be, I'm just going to write it in black from here on out because I'm tired of changing colors. What's mass 2? That's 15 times 9.81. Excuse me for leaving the units out. Minus, the mass 1 is 5.7 times 9.81 times the sine of, what's our angle? 35 degrees, right? 35 degrees right there. So what do we get? What is the net force on the system that it's gonna move in? Okay, so I get that the net force on this system, that is the forces that are competing against each other, that versus that, is 52.3 newtons. All right, now we can't really celebrate quite just yet because that isn't the final answer. All right, but it's going to help us get there. So what that means is that that's a positive number. So didn't we say that clockwise is positive? So it's going to want to move that way. It's going to want to move positively. All right, so it's going to go, in fact, I'll draw it like this, the clockwise direction. All right, so it's going to move that way, which means that there's going to be friction. Well, there always would be friction. We just didn't know which direction the friction was going to be acting because we didn't know which way it was going to be moving. But now we can say, all right, since, let me use a different color here. I'll use purple, I guess. Since this block is going to be sliding up the plane, then that means that friction, kinetic friction, is going to be acting down the plane, opposite the direction of motion. Does that make sense? All right. So now we really find the net force on the whole system, because up until this point we didn't even know what direction it was moving. Now we know, okay, it wants to move clockwise, so friction is going to be acting down the plane right there. Now we can really say, all right, so for our net force on the system, what is it? Okay, well, we have our M2G. All right, that's a hanging block right there. That's in the positive clockwise direction. Minus, I'll go back to color coding it again just to make it simpler. I'll make the M2G red. All right, M2G minus what? Well, minus our M1G sine theta, right? That is our parallel force. Minus what else? Also minus the kinetic friction force, right? Because it always acts in the opposite direction of motion that it's going. So what this will do is give us the whole net force on the system. Okay, if we add all those up. And by the way, the net force in the system, Newton's second law tells us, is the mass of the system times the acceleration of the system. Right? In the first part, there was no acceleration, so therefore everything equaled 0. But now we're going to have an acceleration. The question is, what's it going to be? Okay, so let's find out what the net force is here. And then all we have to do is divide it by the mass of the whole system, that is both masses, and we should have our acceleration of the system. We already know it's going to move clockwise. We just don't know how fast. Okay, so to find our acceleration of the system, and this is going to be your working equation right here, it's going to be M2G minus M1G sine theta, okay, minus the friction force Fk. What is that friction force? Well, we know that the friction force, I'll write it up here, Fk equals mu k times what? Well, you'd normally say times the normal force, right? But we always know that what is a normal force? The normal force is the force perpendicular, right? So you can really say force perpendicular. Which, by the way, how can we write force perpendicular in more detail? That's mu k times mg cosine theta, right? So that's what we're going to put right in here. That's that kinetic friction force mu times the force perpendicular, and the force perpendicular is that, so let's just go ahead and write that in. mg, oh sorry, I forgot the mu k times mg cosine of theta. All right, that is all over what? The mass of the system. Now, this is the net force on the whole system, and so that force has got to be pulling both of those masses. So the mass of the system is really nothing more than m1 plus m2. That's going to be your working equation right there to set up part B in example 8.5. All right, so again, the question asks, what's the acceleration of the system and what direction is it going to go? We already know it's going to go in that direction. All right, the question is how fast, at what acceleration? Well, you've got m2g minus m1g sine theta, that's the force parallel, minus the friction force, which we put together from all these different parts, all that divided by the mass of the system. It should give you your acceleration. Sorry, but right now I don't have a calculator, so I'm going to have to pause this and then give you my final. Well, actually, I can't really calculate it. So hopefully you can do your algebra okay. If maybe breaking these into brackets might help, okay? But that's your working equation that should let you solve for the acceleration of the system. Hope that helps. Let me know how it goes.